All right. So let me first recap. Well, I'll first state the conjecture, and I'll explain what it's good for, and then I'll explain some pathway towards the proof. All of this is a joint work with Sam. All right. So before we get started over field of characteristic P, let me recall two other more commonly known versions of the geometric Langlands conjecture. The first one is the de Rham form, and it says the following. So we consider X is a curve over the ground field K. G is a reductive group. K is algebraically closed. We consider Bun-G. It's just for once, it's not the Fark-Schulze Bun-G, it's the usual Bun-G. And so we consider the category D modules. All categories are derived. And so the de Rham version of the conjecture, so this is de Rham, says the following. We consider the stack of local systems with respect to the Langlands dual group. We consider int-co with condition of, this is the condition of coherent singular support. It won't play a huge role today. So this is the de Rham version. So the Betti version looks a little bit different. So let me emphasize, this is the de Rham version of log-sys. So the Betti version looks as follows. So on the spectral side, you consider also the stack of local systems, but it's Betti version. So when I say Betti, our K is specifically the field of complex numbers. And we consider exactly the same thing. And on the geometric side, we also have Bun-G. And naively, you would guess you would take all Betti sheaves, but that's category is too large. And what you have to do, you consider Betti sheaves, but you impose a condition on local behavior. It's the condition is nilpotent singular support in the sense of Kashivar and Shapira. So if you have a manifold, if you have a subspace in the cotangent bundle, you can restrict the category of sheaves to those sheaves whose singular support lies in this given subset. And nilp is the nilpotent cone inside T star Bun-G, which is the Hitchin space. And so let me just say that this recently became a theorem. So it's a work of many people. I won't say the names because I'll omit someone. I don't want to do this. And as a result, this also became a theorem. There's a formal manipulation that deduces one from the other. And now I'll pass to, so what will be the interest, our interest today, namely, so when our ground field is algebraic closed field of positive characteristic. So Bun-G is the same. So what is sheaves? So here we don't have many options. And when I write sheaves, I mean ℓ-adic sheaves. We really cannot do anything else.
Sorry. What is Betti? Before you were the field K.
So Betti specifically when K is C, complex numbers. And then you take the topological space and you do kind of.
So you have like sheaves.
Very good question. So here, the coefficients can be anything. So here you decouple the ground field and the coefficients. Here they are the same, and here they're again decoupled. So here the coefficients will be Q bar. So Bun-G stays the same. So for sheaves, you don't have much choice. It's ℓ-adic sheaves. And kind of you can convince yourself that you also want to put the nilpotent singular support condition. So if you consider the entire category of sheaves, it will be way too big to have anything to do with the spectral side. Yes. Good? All right. So and now the question is, so this is ℓ-adic. So the question is, what do you have here? So I'll write int-co nilp. But the question is, what kind of log-sys? So here we have kind of facing the following problem. It should be the modular space of ℓ-adic local systems. And if you, at the first glance, it's not clear what it is. How would you vary ℓ-adic local systems as continuous families? And just let me emphasize that it's supposed to be a stack. It's really supposed to be algebra geometric object over QL bar. And the problem is that ℓ-adic sheaves are profinite in nature, and you kind of really you don't know how to feed in this like a positive dimensional algebra. Yet such a gadget exists, and it's called Loxis restricted. And let me, well, it'll play kind of central role in this talk, so let me recap the definition. So let me actually recap all three definitions of Loxis. So what are these? So we proceed Grothendieck way. We say we specify the functor of points. I'll say what hom from spec A to Loxis is in all of these cases. And in each of these cases, it's symmetric monoidal functors out of rep G check to the following target. And the target changes according to the flavor. So let me write. So it's not me, it's the chalk.
It's going to change the ambulance.
But if I break it, will it help? Let's see. Better?
I think the picture on the conference.
Less better?
We'll see.
Yeah, all right, let's see. All right, so these are symmetric monoidal functors to the following target. In the Rham case, you take the category of D modules on your curve, well, valued in A modules. So if you wish, these are D modules on which A acts. In the Betti world, you take just all topological sheaves on X with values in A modules. And here you do the same thing. You just take all ℓ-adic sheaves with values in A modules. Just note that, so you could play a ℓ-adic game over C, and the two targets are very, very different. So here, you're going to take Betti sheaves. These guys have infinite dimensional fibers. So like as a fiber, you can have an infinite dimensional vector space on which A acts. And it does this action of A on the fiber is not locally finite. And ℓ-adic sheaves, whatever they are inconstructible. So if you take the fiber, you may have an infinite dimensional vector space, but an action on A of the fiber is locally finite. And it's a huge difference. So
as such, that meaning A has no ℓ-adic topology.
A is discrete. Yeah, it's within algebraic geometry, not analytic geometry. Yeah. So let me just say what this thing looks like. So, A is a discrete QL algebra. We are within algebraic geometry over QL bar. No, not yet. Not in this talk. So, and you can play this game over field characteristic 0 or over C, and in both cases, here's how Loxis restricted would look like. So let me say it in the Betti world. So you take your local Loxis Betti that you know and love, and then you do the following terrible procedure to it. You take the disjoint union of formal completions of closed subsets corresponding to local systems with a given semi-simplification. So it's a long sentence, let me say it like this. So the stack of local systems maps to the coarse moduli space, which exactly records the semi-simplification. And here you do something awful. You take the disjoint union of closed points, rather of their formal completions. And you take the fiber product. So that's what it looks like. You really broke your beautiful Loxis Betti into this huge, uncountable union, and you might think that you'll got something stupid, but in fact it works. It's very useful. All right. Where is my notebook? All right. Yes, and so I wrote equality, but it's still a conjecture. We know how to prove it for GLN, and we are very close in the arbitrary case. What we are lacking is the theory of singular supports for ℓ-adic sheaves and mixed characteristics. If we had that, we would be able to prove it. But so far, we're one step away. So what I wanted today is this kind of sketch the argument. But before I do that, let me tell you why you might care about such a thing. So you might care about such a thing because this actually leads to the proof of the classical Langlands conjecture in the unramified case. Not even the proof of the conjecture. First of all, it leads to the formulation of what the Langlands conjecture says. So let's suppose you are specifically over FQ bar, but suppose all the objects are defined over Q, so they carry the action of the Frobenius. And you have an equivalence of categories on which you have the Frobenius endomorphism. And in this case, you can take, well, you can take its Hochschild homology, otherwise known as categorical trace. So if you have a category with an endomorphism, you can take the trace and produce a vector space. And let's see what you get. Take trace frob sheaves nilp on Bungie becomes equivalent to trace frob this int co nilp. So first of all, we know what the left-hand side is, and it's quite a non-trivial theorem of AGK-RRV. So it's Arinkin, myself, Kazhdan, Raskin, Rosenblum, and Warshawski. And it says that this is exactly the space of unramified automorphic functions. So this is, let me write it, funct with compact supports. You take this Bungie, remember it was a stack over FQ bar, but with the Frobenius, we can take its FQ points, Frobenius fixed points, and this is exactly the space of automorphic functions. So this is what this theorem says. So this is the automorphic side of classical Langlands. And now let's see what this side is. So let me say something general. If you have a variety with an endomorphism, you can take trace of, let's say, automorphism, trace of phi acting on the category. Let's first take quasi-coherent sheaves. And in this case, well, it's an ABC of categorical trace. You will see that it will be the space of regular functions on the fixed point set. So you can, so we take as Ry our log-sys restricted, and we give the following definition. So log-sys arithmetic is defined to be log-sys restricted Frobenius fixed points. And just wake up, this is the space of arithmetic. This is the modular space of ℓ-adic local systems in the arithmetic situation. Again, a non-tautological existing object, again, for the reason I mentioned. So this is our definition. So in fact, Xin-Wen and Peter gave two other definitions, but you can show that they lead to the same result. So at least experimentally, 3 attempts to define this thing produce the same geometric object. So according to what I wrote here, if instead of int-co, we would have quasi-co, this trace would be, let me just pretend, it would be the space of global regular functions on the stack of arithmetic local systems. And this is almost what Langlands wanted. So if you are in the first grade and you would ask, what does Langlands conjecture says? It says, well, there is a bijection between automorphic functions and Galois representations. But Galois representations form a family, so you don't want to take pointwise. Let's just take regular functions. And that's what you would say. But it's almost correct up to something. So the problem is that we don't have quasi-co. We have this tiny modification, which is called int-co, that has to do with the singularity of the stack of local systems. And lo and behold, the effect that it produces, it's not O, but it's omega. It's the dualizing sheaf. But that's what Langlands conjecture, well, that's what the classical Langlands conjecture is supposed to say. And if you believe geometric Langlands, it actually says that it's not a conjecture, it's a theorem. So that's why you may want to care about geometric Langlands characteristic P. All right. All right. So now we'll launch the proof. Are there any questions?
What does the Sommiger mean from like the classical point of view?
Oh, it's just dualizing sheaf.
No. I don't. I'm not asking for the definition. I'm just saying if I'm
Mysterious.
let's say I'm in first grade and I'm still learning.
Mysterious. So here's the exercise for the first grader that I wasn't able to do. Take SO2 apart from genus zero, in which case it's easy. And like in this case, we kind of understand how automorphic forms look like for SO2 and try to match it with this. It's non-trivial exercise. Like it says something very, very concrete, but how to match it to the description of like automorphic forms via Eisenstein series, like oh, by the way, on the cuspidal part, on the irreducible locus, omega is O. Like on the cuspidal part, it's really kind of, as the first grader would say, just for every local system, it's the Eisenstein part that messes things up. And it's not easy to analyze.
So this has to wait till second grade.
I'm afraid, yes. Correct.
So very slightly
Then
different.
what Langlands told us with Eisenstein. Yeah. It's not L2. It's really compactly supported functions. Laurent.
What's the problem with nilpotent angular support on Bungie? I mean, the line is this theorem of Beilinson, the school in Tokyo, and Takashi Saito, and also this was solved.
Yes. So this is
well defined.
It is well defined on the geometric side. So that two nilps, we're talking about nilp on the left. Yeah.
Okay. And for this respective the moduli space, I mean, this doesn't solve the problem. All observation by Beilinson for GL2 that has been upgraded by this student of Chaudhary recently for GLN, that the number of points looks like the number of points of an algebraic variety.
Yes. So can you repeat the question again?
There is this whole theorem due to Beilinson that it looks like there is a moduli space of local system. If you count the number of points,
yes.
Stress formula. It looks like there is an algebraic variety, but the construction of this restricted moduli space doesn't give any insight.
Well, no, it is the moduli space, and then you can combine, you can count the points on that versus what Drenfeld predicts. And
yeah, but you replace the space by it's a disjoint union of formal completion.
No, that was for restricted. And then when you take arithmetic, you take fixed points of the Frobenius, but because this thing is stacky, so
that's the point.
Yeah, because it's stacky, it becomes. So what happens is the Loxis arithmetic is a genuine algebraic stack. It has no formal directions. It's really kind of it's algebraic stack of finite type.
It's not a formal algebraic.
It's no longer. Somehow trace of Frobenius, fixed points of Frobenius eat up all the formal directions.
Classical one derived.
It's highly derived. It's highly derived, and that explains the difference between O. If it were classical, there would be. In this world, there will be no difference between O and omega. Yeah. Yes. Say again?
Yes. So this is the brightness.
This sacred over cuba. So let me not go into there.
Q versus QA. It's completely different.
Yeah. Yes. Okay. All right. Please. It's forbidden.
What was the question?
What happens if X is not projected? No, it's next talk. It's forbidden for the next 45 minutes. So we are doing unramified situation. Yes. So Sam will talk about the ramified situation. It becomes much more conjectural. We see a path towards what should be done, but you'll see it's.
When we just grade.
Wait till second grade. Another 45 minutes. Yeah. So this is a ramified in an hour.
It's not.
No, it's fine. No, it's. No, it's what's called quasi smooth. The cotangent spaces live. So smooth means cotangent spaces in degree 0. Quasi-smooth in degree 0, -1. This is 0, -1, -2. Yes, but if you look at the structure, because it's -2, if you look at the structure of sheaf, it lives in infinitely many degrees. Like typical example, you take the symmetric algebra on the generator in degree -2, and you get the polynomial algebra non-negative. It is perfect. Yeah. All right. All right. So now we'll launch the proof of this thing. But first, I want to say a few words about the sheaves nilp. So, like, first comes the following theorem. Historically, it's the first theorem we prove in Langlands. It's a spectral decomposition theorem. So, and it says that we have a canonically different. So, it says the following: that Hecke functors, in the sense that was described in the previous talk, combine to an action of this monoidal category, quasi-co, loxis G-check restricted, on this category. It's not just some random action. Again, it comes from the Hecke functors. Let me just say that we have parallel theorems in both the Betti and the Rham contexts, and also Farc-Scholze. So in the Betti context and the Farc-Scholze context, the fact that Hecke functors combine to such a thing it's not tautological, but it's easy. So in the Rham context, it's crazily complicated. It's not that the proof is long. You use a lot of extrinsic tools. You use representations of affine algebra at the critical level. And for that reason, in the Rham setting, I don't know. So it's like, it's very, very subtle. I don't know how to generalize this thing to slightly more general situation. And in this restricted setting, it's not as bad. It's basically the same price as the Betti. So we have this. But in fact, you have more. Just bring my. So by the way, this on its own recovers Beilison's theorem in the unramified situation. So if you take this, and if you hit this action with a trace of the Frobenius, you will exactly see the action of the excursion algebra on automorphic functions. And well, it's gonna. All right. So, but now I want to say a little bit more. So we'll use the construction called Beilinson's projector. And so forget all of this. So fix sigma a local system. So you can consider the category just of all sheaves on Bungee, and you can consider the category of Hecke eigensheaves with respect to sigma. And what Beilinson constructed some 30 years ago, so there's a forgetful functor, he constructed a left adjoint, and it's given by a very explicit integral operator. So you kind of you apply the Hecke functor corresponding to the regular representation of G-check, twisted by sigma over all points of the curve, combined in what's called the round space, some huge thing that we could denote it by p sigma. It's some explicit generalized Hecke functor. So you can do it for an individual local system, or you can do it for a family of local systems. So you can do it for families, and in fact, you can do it for the universal family, namely this loxis restricted. So there exists a functor, let me call it P universal. It's an endofunctor of sheaves of Bungee. And again, it's some huge colimit of Hecke functors. And so the whole point is that this is in fact the projector onto the nilpotent category. Yep. So what results from the spectral decomposition theorem is that this universal Beilinson projector maps all sheaves to sheaves with nilpotent singular support and acts as identity as on sheaves with nilpotent singular support. And so this kind of thing is used throughout our construction. All right, so using this, we'll now try to construct a functor in one direction. Oops, and now what do I do? It's gone. Oh. So Sam will not like it, but I will. So it's a good tradition in Langlands to go from geometric to spectral, but I'll violate the tradition. I'll go from spectral to geometric. And he's in the audience, he cannot object. So I'll go from here, sorry, intco to this sheaves nilp. So I'll even cheat. So I don't want in this talk to worry too much about this nilp. Let me construct the functor from the subcategory, which is the original quasi-cope. So to do the entire thing, you have to do something with Eisenstein series. I don't want to worry about it now. So let me construct a functor from here to here. But hey, this category, as we just said, is acted on by this. So if you want to construct a functor out of it, all you have to do is to specify one object. So let's find this object that we want. So the datum is equivalent to specify an object. In here. All right. So let's recall, well, we have to invent this object. Let's recall what we do in the more familiar de Rham situation. In this case, we know what this object is. It's what called, some people call it the unit Whittaker sheaf. I recently decided to call it the vacuum Poincare sheaf. It's a very specific guy. Let me call it Poincare vacuum, in this case, in D mod. So, and in the de Rham situation, that's the object and you act on it. So let me just briefly tell you what it is. So you consider, you know what, I won't do it. It'll be too much of a distraction. Ask me later. It's some specific guy. Well, if this is what we do in the de Rham situation, why don't we do the same in our ℓ-adic world? So I want to define this functor. So this object is defined also in the ℓ-adic world. So the object will be this Poincare vac. Yes. It's the same. Well, always. It's like I'm doing large categories. Quasi-co is the int completion of perf. Yeah, it's just large versus small. Amounts to the same. So again, my functor is defined by action of Poincare, the vacuum Poincare object. Everybody happy? Oh, say again? For the vacuum Poincare? Okay, I'll tell you what it is. So
are you doing the de Rham one now?
So I said in the de Rham, you do this. This object makes perfect sense in the ℓ-adic, and I take the same guy and act on it.
But you have to find it.
Okay. Okay, let's strike a deal. I'll define it for SO2. So here's how it's defined. So here is my Bun G, and I consider the following twisted version of ban n. N is the maximum nilpotent. So usually for SL2, ban n classifies extensions of O by O. These are rank 2 bundles which extends of O by O. This guy, I call it twisted by omega. It classifies extensions of omega minus 1/2 by omega 1/2. I twisted by half canonical bundle. So now this variety, exactly because of this twist, by Serre duality maps to the affine line, namely the class of this extension. X1 from here to here is the same as H1 of omega, which is canonically A1. What you do, you pull back Artin Schreier and push forward. So this is the guy. This is the Poincare sheaf. So you may think that it involves the Artin Schreier, but in fact, it's a delusion. It can be eaten up. So in fact, it can be defined even when k has characteristic 0. So you don't need the exponential. So Sophie, and you can imagine what you do for an arbitrary group. You do it along every simple route.
So, what you mean by arbitrary moving characteristic?
Let's say characteristic P, it's okay, yeah? So, and it's defined in D modules or in Artin Schreier characteristic P. So that's your object. So, and I want to act on it. And again, I'm asking the question, is everybody happy? Say again? Exactly. So it doesn't make sense because we wanted an object with nilpotent singular support, and this Poincare vac emphatically doesn't have a nilpotent singular support. If you take your group to be GM, in which case Bun G is just the Picard, this vacuum Poincare is the skyscraper at the unit, the unit point. And in the case of GM, nilpotent singular support means lease. It should be local system. So like the delta function is really not lease. So it's not a kosher object on which to act. So what do? Well, you have Beilinson's projector. So you take P universal applied to vacuum Poincare. And so that's the object on which you act. So that's your functor. All right. So again, modulo this difference between int_co and quasi_co, I've constructed a functor in one direction, and now I want to show that this functor is an equivalence. Where am I? My phone. Yes. Right. And so the way I want to show that it's an equivalence, I want to deduce it from some situation that I know. So first of all, I claim that the fact that we know Betti geometric Langlands over C, it actually formally implies that we know ℓ-adic geometric Langlands over algebraically closed field of characteristic 0. So Lefschetz principle gives you that. So we know ℓ-adic in characteristic 0, and we want to deduce ℓ-adic in characteristic P. And what we're going to do, we're going to play the specialization game. So you choose a DVR so K, our ground field characteristic 0 is the residue field. So we denote by K the fraction field. And denote by K bar its algebraic closure. And I denote by S the spectrum of K eta, the spectrum capital K, and eta bar, the spectrum of K bar as in Song-Stock. So now you have a curve over the residue field. So thankfully, we are in dimension 1. There's no obstruction to deforming it over R, and just have the whole situation defined over spect R. So you have this gadget Bun-G R that lives over spec R. So to here we have this eta bar mapping. We call this map J bar. This is the map I. And you can base change things and play the usual nearby cycles game. So we introduced our functor psi that goes from sheaves, a priori all sheaves. Let me call it algebraically closed generic fiber to Bun-G on the special fiber. And so this is the functor J bar lower star, high upper star. So our proof is based on studying the properties of this functor. So a priori, it's some beast. So nearby cycles are notoriously unpredictable. And the first thing you want to show that it actually sends the category with nilpotent singular support to the category with nilpotent singular support. Otherwise, what chance do you have to use it? So theorem, functor psi sends sheaves nilp from Bun-G eta bar to sheaves nilp. So how are we going to prove such a thing? So in fact, it turns out to be pretty easy. So lemma, functor psi commutes with Hecke functors. So, and by the way, because we are dealing with two algebraically closed fields, our log sys's are over eta bar and over S are isomorphic. So log sys restricted. So as a corollary of this, functor psi commutes with this Beilinson's projector. So P universal psi is psi P universal. And that immediately implies the theorem, because if you plug in a thing with nilpotent singular support, P universal acts on it as identity. You apply psi, it's the same as a psi, apply P universal, and that just projects on the category with nilpotent singular support. So that proves the theorem. All right, so let's use more of this functor.
Looks slightly different from special and generic fiber because of the pro keyboard.
Yes, but I mean it's ℓ-adic local systems.
Sure, but so I mean, do I have an ℓ-adic representation?
Let me skirt this question.
So what happens is like, the fundamental grouping characteristic P is smaller than the fundamental grouping characteristic 0. So what you can see is that it's like most restricted in characteristic P, it's just a union of connected components with a guiding characteristic 0. So what that should right here is not really like P universal on the source, we should write it.
Yeah.
Sort of structure sheet. It's sort of like having a motor like on the source.
Yes. Yeah, integrate not over big log sys characteristic 0, but integrate over those connected components that come from the special fiber. So next theorem. So we have our functors. So we have int co nilp log sys. Let me put eta bar going to sheaves nilp Bungie eta bar. This is the Langlands functor in characteristic 0. So here we have our functor of nearby cycles, and here, well, I wanted to cheat and write identity. What I mean is it's a functor that you just, it's identity on those connected components that match, and you send to 0 all other connected components. Let me just henceforth, when I write this, I'll just mean the unit of connected components that come from the special fiber. So I claim that this diagram commutes. Okay, so we have to prove it. So now let's recall how the functor was constructed. Well, I only really constructed the functor not on int co, but on quasi co. So let's do it like this. So what was the functor? You were acting on a specific object. So here, Sophie should object, because here I'm really in characteristic 0. You should ask me what do I actually mean by the Artin-Schreier sheaf in characteristic 0? If you're going to ask you, I'm going to answer you. Unfortunately. So here's the trick. So this is bun n. It maps to bun g. And here it mapped to A1. So what we did, we pulled back the Artin-Schreier and we pushed forward. So that was our recipe. But in fact, note that on bun n, GM acts. So namely, you have this extensions, and you can act by you can act by scalars. So this map factors through bun n mod GM. So therefore, you can replace this diagram by this diagram. So you take Artin-Schreier, push it forward, pull it back, push it forward. So when you take Artin-Schreier and if you just average it with respect to GM, you get something tame. So namely, if you Schrieg average, you get J lower star, extension by star from the open locus. So that's how you get rid of the wild things. I call it replacing the Whittaker model by Kirillov model. Whatever. Kirillov didn't object to this. So that's to say that Poincare makes sense in characteristic 0. So let's prove it. So lemma. This lemma is before I pass to nilpotent singular support. I claim that psi of Poincare vac eta bar is Poincare S. And the proof is, so I claim that so this Poincare makes sense over R is ULA. So this Poincare sheaf behaves very nicely as you vary the base. So take this lemma and hit it with Beilinson's projector. So this proof of the lemma, and then do P universal Poincare back. And as we again commute nearby cycles, sorry, P universal Poincare back, and you obtain your result. So we have this. So we have some weak compatibility between the functors in characteristic 0 and characteristic P. And we know that this guy is an equivalence. And again, so let me only keep those connected components of this that's mapped bijectively, and this, according to the spectral action, this category splits as a direct sum. Let me also only keep those connected components. But still, you're very far from the proof. So this is an equivalence. Let's say this is an equivalence. If you want to show this an equivalence, you better prove something about this functor. And here comes kind of the main idea. So theorem 3. So this functor psi is quotienting. Well, in the sense of Verdier. So like the category in the special fiber is actually the quotient of the category in this generic fiber, but the full subcategory. So I'll indicate the proof in the remaining time. So this, all it says for now is that this is a quotienting, which is actually quite a lot. It's already a lot of information. It doesn't show that it's an equivalence. And in fact, it really doesn't. We can only prove that this functor is an equivalence in the case of GLN. Otherwise, as I said, we're still missing something, but it gives quite a lot. So in fact, let me tell you, let me jump to the end. So what we can prove is that this functor is an equivalence between our desired target and int conilp over log sys g check restricted prime, where all I mean by this, it's a substack, which is a union of some of the connected components. So what we don't know is that this functor doesn't kill some of the connected components. So that's what we have for now. And for GLN, you can show that actually all of them appear. All right. It's an equivalence. So we can prove this equivalence. We show that it's not all log sys restricted, but some part of it. All right. So in the remaining time, I'll prove theorem 3. Let me see. All right. So, general question. Suppose I have a functor between two compactly generated categories, C and D, functor F. By the way, kind of in the same way as we proved theorem 1, you can show that this functor F preserves compactness. And suppose the functor F sends compact objects to compacts. What is like the explicit criterion to see that this functor is a quotienting? Rhetorical question. Not rhetorical, question to the audience. So can you give me the algorithm? So what I want to, so let me make it more precise. I claim that you can write exactly one map, and this map is an isomorphism if and only if this map is a quotienting. Do you guys know which map that is? Please. Anything? No. No. Yes. Oh, yes. Localization means that apply with the right, compose with right adjoint. No, I don't want that. But it's a. it's a correct answer, but that's not the answer I want. So let me tell you which answer I want. So I said this category is compactly generated. Let's consider the dual category. So remember, so C is ind of its compact objects, and the dual category is ind of the opposite category of compact objects. And same for D. And so the functor F induces a functor, let me call it F op between the dual categories, namely just restrict F to compact objects, pass to the opposite functors, and ind extend. So in other words, F opposite is the following. You take the right adjoint and take its dual functor. So that's what F opposite is. Some general construction. You can also think of it as Verdier conjugate. All right. So this is something very general. Now consider C tensor C check. It has a unit. And consider D tensor D check. It has its own unit. And so exercise, there's always a map from F tensor F op applied to the unit of C. It's an object in D tensor D check maps to UD. And so the claim is that F is quotienting if and only if this map is an isomorphism. So that's exactly what we're going to check in this situation. So again, general lemma in DG categories.
Basically, because the comment before was exactly right. D tensor D check as interfunctor D, and this is the map from the left hand. Well, the right hand side is D, and the left hand side becomes right adjoint.
Now, think of a compact object inside D. No, it's like compact object tensor, its opposite maps to the unit functor in a compactly generated category. The direction is right.
Oh, yeah.
Yes. All right. But hey, now we have to. So the problem became more complicated. So now we have to. So C is sheaves nilp on the generic fiber. D is sheaves nilp on the special fiber. We have to find those dual categories. What are they? And so and here comes like the input from, again, from AGK RRV. So what it says is that sheaves nilp Bun on anything is self-dual. In a very specific way. So I'll tell you what the unit is. Well, you can take the tensor product of categories on general grounds. It will be a full subcategory inside sheaves on Bun G times Bun G. And now you perform the following procedure. Take the diagonal, take the delta lower shriek of the constant sheaf. So I denote by E the field of coefficients. In this case, is QL bar. It's an object sheaves Bun G times Bun G. It's most definitely not an object of sheaves on Bun G, tensor sheaves on Bun G. The categorical unit formula does not hold in the ℓ-adic context. Sheaves on the product is not the same thing as the tensor product of categories of sheaves. It belongs here. But now you do the following. You apply Beilinson's projector along the first factor or the second factor or both, and it's going to be all the same. So this is an object here, and the theorem from AGK RRV that actually belongs here. So miraculously, after you hit it with Beilinson's projector, and this theme will recur in Sam's talk, it splits as a product. It belongs here. And the claim is that it serves as the unit of the self-duality. So this is the unit. And so we have to check the criterion. What does this criterion say? Well, it says that psi, well, in this case, we are on Bun-G times Bun-G, applied to this unit at the generic fiber is the unit of the special fiber. And again, this unit is got by Beilinson's projector. So what you want to deduce it from is that it happens before you apply Beilinson's projector. The psi of this constant sheaf on the diagonal, generic fiber, is constant sheaf on the diagonal on the special fiber. And where will you get this from? Well, again, ULA. So the claim is that this guy, if you consider it's over the entire ring, is ULA. Done.
If we come back to the good old days when I was not organizing the conference but a seminar in Orsay, you explained to us the case of a skyscraper sheaf over geometrically irreducible local system, how to descend it. There is descent argument using local acyclicity, it's all up. I know.
Yeah.
At which points it is done? I mean,
So that was GLM.
that was GLM.
That was GLN. So as I said, it's a theorem only in GLN. But in the case of GLN, so without the theory of nearby cycles, to prove the theorem for GLN, you still have to show the existence of Hecke eigensheaves for GLN.
Oh.
And that is that old work. For GLN, we're still hoping to circumvent all of this. So if the theory of Seiter's nilpotent singular support was available in mixed characteristic, we wouldn't need any of this. The point is that the problem is it's still not. So if you are over spec R, you have a variety of spec R, you have a ℓ-adic sheaf,
yes.
We don't know what it means to what singular support is. In characteristic P we do,
yes.
But not in mixed characteristics. Yes, if we had that, we wouldn't need that argument. But so far we don't have it. Say again? This singular support. So so here's the situation. Take your Hecke eigensheaf in characteristic 0. And so the problem is that it may be clean when you try to extend it like across a special fiber. But so just some formal properties of singular support will tell you that the singular support is perpendicular to the cotangent bundle to the special fiber. So this cleanness wouldn't be possible if the theory of singular support existed. I can answer this in more detail.
If you do like Arnold reciprocity for transforms, will you be able to introduce?
Yes. So let me just say that I said that this does this. It has, you can take the trace of the Frobenius, it will tell you exactly what automorphic forms are, and you will see that only arithmetic local systems that correspond to those geometric reducible components appear. So if you knew that all components appear, you would be done.
So for GLN, you are using the contours theorems in it.
No.
Well, how do you know that all local systems appear?
So that was the old work of Drinfeld that was generalized by kind of my co-authors and myself.
Oh, this one, oh, okay, not the theory.
Yeah. So like we proved the existence of automorphic sheaves. It's
So use the contours theorem.
one could.
Yeah.
So one, like for GLN, one could use Laurent's result, so just Lafog to just finish the argument, just by what Tony says. But we don't need to resort to that. So you can do it by geometric methods.
Okay.
Yeah.
So is it important that the coefficients are characteristic 0, or what have we get about?
See, I'm a number theoretical terrorist. I refuse to think model.
You wrote a paper model.
Show me this paper. No. So I just, okay. So I don't have it in my brain now, but I'll be happy. I need to rewire myself to answer this question. But maybe Sam has more ready answers. I just.
Then it assumes that theory exists.
No. So I just so not in my head currently.
Like, I don't know. Like,
No, I would say we're using the characteristic zero theory, which we ultimately get in the story. So you should then.
okay, yeah, that's an answer. Like,
That's an answer, yes. Our methods heavily use the Rham theory.
is there any hope?
No, it's such a deep path.
You have this conjecture in the book that, you know, there's some categories to be adapted to spectral decomposition or whatever. And you just prove it in that particular case going to be the Rham theory.
Betti.
Betti, whether, yeah.
But so for GLN, so you can prove the original GLC by other methods. So, and that should work in mod L. So for GLN, there's a path. So like what Sam is saying, we're using the Rham theory. That's really for groups other than GLN. For GLN, you can prove the original GLC as is.
Yeah, I think somebody wrote a paper about that.
Yeah. Anyways, so for GLN, yes. For other groups, we don't like. For other groups, we don't know the existence of. Essentially, we don't know the existence of eigensheaves, and the existence of eigensheaves in characteristic 0 ultimately comes down to affine algebras. So I give you a local system for G check, produce for me eigensheaf. We don't know how to do it.
More questions?
This duality, in our case, is chanceux, I guess, is the Beilinson derivative.
So that's what Peter told me.
Yeah.
Let me just say, so this is the unit. Let me tell you what the co-unit is. It's much simpler. Tensor together take compactly supported cohomology.
Yes, but the unit, it's the equivalence.
Yeah, so like the pairing is very easy. Just it's the usual one. Tensor take cohomology. So and then I guess it should be exactly as yours.